We will now talk about the strong ground motion part. Let me share the screen. All right, can you see it now?
Yes.
All right, so hello everyone again. This is Askan from METU Ankara. We have been working on effects of strong ground motions and their actually preliminary studies, including the intensities and predictions, comparisons with the ground motion prediction models. And we will have actually 6 speakers today. We will have 35 minutes of talks with 5 minutes question and answers. I will be chairing this session with Dr. Basil Margaris and Professor Zeynep Gülerce. First, I would like to make you listen to a voice message from Sinan Akkar, who could not be here today. For a few seconds, please.
Dear friends, dear colleagues, hello. Unfortunately, I'll not be able to attend the meeting due to a previously made arrangement for an outdoor activity. We could not change the dates of it, so I'm far away from my desk. It was great participating in this reconnaissance report, and many thanks to the coordinators and in particular to the ground motion working group. I wish you great success in the webinar. Cheers.
Okay, then Basil, I'll give the word to you.
Thank you very much, Ayşegül. Hello, everybody. On behalf of the coordination group and the Greek team, I thank you, and we thank you, the organizing committee, and especially Professors John Stewart, Onder Cetin, Tassos Sextos, and George Milonakis for giving us this excellent opportunity to work all together against this destructive earthquake occur in the cross-border between Greece and Turkey. Now I am presenting Professor Zafiria Roumelioti from Patras University for the first presentation. Rula, the floor is yours.
Thank you, Basil. Okay, good afternoon. Good morning to US. I hope you can all see my screen.
Yes, we can see your screen.
Just a minute, please. I'm sorry about this. I have to minimize to go to. Okay. Okay, so my part of the overall presentation is about the strong motion data of the Samos earthquake from stations in Greece. I will briefly present the collaborating networks, what kind of data is available and which part of it was included in the GEAR collaboration. And I will start with a map showing the two nationwide strong motion network that we have in Greece. With black color, you can see the stations operated by the Institute of Geodynamics of the National Observatory of Athens. And as white triangles, you can see the stations operated by the Institute of Engineering, Seismology and Earthquake Engineering. So we have a pretty good coverage of the mainland, but in the Aegean Sea area where the Samos earthquake occurred, the distribution of the stations is rather sparse. So both networks operate two generations of strong motion stations. We have the new generation stations shown in this map in red color, which are mostly equipped with SIM-G5T sensors and provide continuous data. And we have older generation stations with sensors mostly of lower resolution that operate in trigger mode and are shown in dark gray color in this map. coming to the October 2020 earthquake. In this version of the map, we can see the stations that recorded the event. So you can see they're mostly red stations because the older generation stations were not triggered, with the exception of 2 located on Samos Island. The modern station recorded the event up to quite large distances, and you can see the distribution here. And the azimuthal coverage is mostly to the west, but the Eastern Gap is very nicely covered by the Turkish stations, as our colleagues will show in a while. So overall, we have 98 records. And in the frame of the GEAR collaboration, we decided to work with 2 subsets of data. The first subset includes the records obtained within a distance of 1,000 kilometers from the earthquake source. And we use these records to compare time histories and spectra. And in this subset, we contributed the 2 records that we had on Samos Island. And the second subset is, involves the records up to 200 kilometers from the earthquake source. And there we contributed 11 records. So I won't go into the details of these records. They will be shown in the presentations to follow. I would just like to give a few pieces of information more on the 2 near-fall records that we have on Samos Island, and more specifically in Vathi, the capital of Samos. So here we have the fault. Vathi is somewhere here, and this is where we have the 2 collocated stations, and SMG1 and Sama. So both stations are installed at the basements of 3-story public buildings. And these buildings are at a distance of about 300 meters apart. We have velocity profiles measured after the Samos earthquake at these 2 sites, and site conditions are considerably different. I believe that pertinent information will be presented by Panagiotis Pelekis. And according to the preliminary simplified source model that we adapted in the GEAR report, these stations are considered near fault no matter what distance metric one adapts. And they both lie on the footwall side of the causative normal fault. So looking at the data, these are the data from station Sama. You can see here the time histories of the 3 components, the Fourier amplitude spectra of acceleration, and the response spectra. And I will just make 2 notes. One is on this energy high that we observed in one of the 2 horizontal components in the period range from 0.4 to 0.7. And we can see as a bump here in the Fourier spectrum as well. In this area, in this period range, it surpasses the design spectra of EC8 and the National Building Code. And another interesting feature, quite opposite, is this spectral sag that we can clearly see in the vertical component here, but we can also see it in the horizontal components at certain directions. The picture is quite similar at station SMG1 because at these close distances from the fault, we expect that the source will be the dominator and it will mask all other effects, such as the side effect, which is different, as I mentioned earlier. If we take a look at the particle motion plot at this site, we can see the strong imprint of the source. For example, here you can see the vertical plane that is oriented from south to north here. And we can see that the maximum displacements are aligned in a direction that is perpendicular to the fault plane projection, let's say. So to wrap it up, these 2 records that we have on Samos are not of the best quality as we would wish, but still they carry important information that will make us understand the physics of this event. And I will conclude my part by reminding to everybody that strong motion data from stations in Greece are available online through the ADA node and through the links that are presented here and included in the GEAR report. Thank you very much.
Okay, now we will move on with Dr. Yannis Kalogeras.
Hello, everybody. I would like to express my sincere thanks to the organizers who invite me to participate in this work and give me the opportunity to cooperate with a lot of scientists. Our next speaker will be Dr. Dimitris Sotiriadis, he's an expert in soil structure interaction, and he will present the new GMPs, the new Greek GMPs, in comparison with the strong motion data from Samos earthquake. So, Dr. Sotiriadis, you may begin.
Thank you very much for the introduction. I hope you can hear me.
Yes, we can hear you.
Okay. I will share my screen now. Do you see my screen? Please confirm.
Yes.
Okay. So during this short presentation, we will discuss about the preliminary evaluation of the predictive performance of ground motion prediction models which are applicable to Greece. This evaluation is performed against the data recorded during the earthquake occurred near the island of Samos. For this cause, we used strong motion data from 77 Greek and Turkish stations located within 200 kilometers from the rupture plain. We consider 3 GMPMs, namely, the first one is the model proposed by Boer et al., namely BEA-21, which is the latest GMPM for shallow earthquakes in Greece and has been developed through modification from the BSSA-14 model. The second one is the one proposed by Boer, is the BSSA-14 model for the region of Italy, where the features of strong motion are similar to Greece. And the third one is the model of Skarlatoudis et al., developed in 2003, which is widely used in Greece. On the slide, on the left figure, we can see the distribution of data with respect to VS30. We can see that most of the stations are classified inside class C and B according to the Eurocode 8 classification scheme. On the right figure, we can see the distribution of recordings with respect to the Joner-Boer distance. The majority of data were recorded at distances greater than 50 kilometers, and only few near fault stations record the event. Actually, there were 2, the ones in Samos Island. So we initiate our evaluation of distance attenuation of PGA values. On this figure, the blue markers correspond to the data at stations with VS30 smaller than 360 meters per second, whereas the red markers correspond to data at stations with VS30 greater than 360 meters per second. Correspondingly, the blue curves of the BEA-21 model shown on this figure correspond to a VS30 value equal to 270 meters per second, whereas the red one corresponds to rock conditions, namely a VS30 value of 800 meters per second. The dust curves on BEA-21 model include a bias parameter which has been attributed to a systematic overestimation of the global ground prediction models in Greece, which is attributed to either regional features or to soil structure interaction effects. On the other hand, the solid curves do not include this bias. Regarding the distance attenuation, we can observe that the BEA-21 model is quite consistent with what was recorded during this event. A similar situation is observed for the BSSA-14 model, with the difference that BA221 seems to be a little better in long distances than BSSA 14. The last figure presents the Skarlatoudis et al. Model, which is based on epicentral distances rather than Joner-Bourg distances, and its SAT amplification is based on soil classes rather than absolute VS30 values. So in this model, we can see a consistency in distance attenuation of PGA up to approximately 100 kilometers, but for longer distances, there is a significant deviation. The evaluation of distance attenuation is performed also for spectral accelerations at period of 0.2 seconds. We can see a similar situation with the PGA for the BA21 and BSSA 14 models. And it was also performed for the spectral accelerations at period of 1 second. Here we can see that some stations which are located at the region of Izmir show significant amplification with respect to the estimates of GMPs, which has been attributed to possible site amplification effects. We also performed the preliminary evaluation of residuals of between the recorded ground motion and the median estimates of ground motion prediction models with the site-specific VS30 values. We can observe on the first figure for the BA21 model that including the bias parameter, which corresponds to the red markers, improves the matching between the recording data at the near-fault stations. Also, for all of the models considered herein, we can see that for at stations at distances between 30 and 80 kilometers, there is a significant underestimation of the ground motion, which may also be due to significant sound amplification effects. On the other hand, for longer distances, for the BA21 and the BSSA 14 model, we can see that the residuals are fair enough and their values oscillate around the zero value, whereas the Skarlatoudis et al. Model consistently overestimates ground motion. The evaluation of residuals was performed also for the spectral accelerations of 0.2 seconds and 1 second. We can also see here that we can confirm this underestimation of ground motion from the models we used at distances between 30 and 80 kilometers. The residuals seem to be higher than the PGA values. And this is where my presentation ends. Summarizing what was shown in this presentation, we saw that the BSSA 14 model for low Q regions and the BA21 models seems to be consistent in terms of distance attenuation with the recorded data of Samos Island earthquake. The residuals between the recorded ground motion and the median estimates of GMPMs are fair for most of the stations considered. However, at several stations, at distances between 30 and 80 kilometers, the recorded ground motion is systematically higher than the median estimates of the selected GMPMs, possibly due to significant site amplification posed by possible Bayesian effects, which of course require some further investigation. Thank you very much.
All right, we thank you very much, Mitris. Now, next, I will actually share the slide. And we will have 2 other speakers. Okay, can you see the slide now, I wonder? Can you see my slides?
Yes. Yes.
All right, yes, perfect. Yes. Okay, now next is Dr. Şakay Karimzadeh from METU, followed by Professor Zeynep Gülerce, and then Burak Akbaş, and then I will conclude. Please, Dr. Karimzadeh, floor is yours.
Thank you, Dr. Askan. I would also like to thank the organizers of this webinar. So good afternoon, everyone. Let's start with the strong ground motion network in Turkey. some information on the stations that recorded the event, followed by the felt intensity distribution. So this slide shows all available strong ground motion network in Turkey operated by AFAD. There are in total 850 stations where 679 of them are active. Information regarding these stations can be found in the new official website of Disaster and Emergency Management Presidency of Turkey, AFAD. So next slide, please. At most of these stations, VS30 values are known, and to all ground motion records provided by AFAD, screening, windowing, and filtering procedures are implemented. Note that the data regarding to Samos earthquake is filtered between 0.1 and 25 Hertz. Next slide, please. So this figure illustrates the seismic hazard map of Turkey. This map demonstrates the highest level of seismic hazard nearby the two major tectonic zones, including North Anatolian Fault Zone and East Anatolian Fault Zone. In addition, as you see, the seismic hazard is also pronounced high in the western part of Turkey, including Izmir region. As you know, the Samos earthquake hit the Turkey's Aegean coast, so the western province of the Izmir region. So next slide, please. So the Samos earthquake was recorded by a total of 83 stations, all of them located within an epicentral distance of less than 200 kilometers. Among these stations, 33 of them have epicentral distance of less than 100 kilometers. So this map shows the epicenter fault plane and the location of the 33 stations. As you can see from this figure, there is not many near field records in Turkey for this event. So for more investigations, we selected, let's say, 6 number of stations. So next, please. So this table lists some information on the seismological parameters at the selected stations. The 2 stations, the bottom ones, with the ID 0905, in Kuşadası and 3528 in Çeşme region have the highest PGA levels as approximately 180 and 150 respectively, yet note that in these regions no structural failures were observed. The other top selected 4 stations are located within the Izmir Basin. They have high levels of significant duration as well Hausner intensity. This observation could be attributed actually to a combination of basin effects as well site amplifications. In addition, as you can see from the table, among these 4 stations, the top 4 stations, 2 of them with the IDs 3530 and 3514 are located in Bayrakli region, where structural failures were observed. So next, please. So in this slide, the time story is Fourier amplitude spectra and comparison of response spectra with the seismic design codes, including 1975, 2007, and 2019 are plotted. So it can be seen that at the selected stations, the observed spectral values are below the code levels, except at some points. Actually, these points are observed at the bottom 2 stations within the short period range, where the spectral values are a little bit above the values corresponding to the 1975 design code. In addition, at these 2 stations with shortest distance to the epicenter, short period amplifications are observed. It is also noticeable that no structural failures were observed in these regions. When the top 4 stations within the Izmir Basin are considered, actually long period amplifications are observed. Note that 3 of these stations have soft soil conditions, you can see in the table, have soft soil conditions, while one of them with the ID 3514 has located on a stiff soil type. Finally, actually, we can say that observation of line period amplifications at the stations located in Bayrakli region are consistent with the fundamental period range of the collapsed structures. So next, please. And finally, let's take a look to the felt intensity distribution of the Samos earthquake. Here in modified Mercalli intensity distribution plots are given. The left panel shows the MMI distribution provided by the AFAD Rapid Earthquake and Damage Estimation software. The right one is prepared by our team, where the local correlations between MMI and peak ground motion values are used. This plot is same as actually the red box in the left panel. So from both figures, it can be seen that at the coastal regions, higher MMI values are observed compared to the land. The maximum values in the right panel are predicted as 7 and 8 at the coastal areas of Izmir, including, let's say, Bayrakli and Samos Island, respectively. In addition, a higher MMI level is predicted in the Seferihisar coastal part, where the tsunami was observed. So I stop here and give the word to Dr. Gülerce. Thank you.
The next slide, please. Thank you, Professor Dr. Karimzadeh, for this wonderful presentation. Hello, everybody. I'm Zeynep Gülerce from Middle East Technical University. I just would like to say a few words about the ground motion models and why we included the comparison of the data with the ground motion models into this report and why this is important. Then I'm going to give the floor to our young colleagues once again to show you the results. I have a distinguished members in here from the community that know everything about the ground motion models, but we also have younger colleagues and students here. So I just wanted to define that the ground motion models, or the GMPs, are the tools that we use to convert the earthquake scenario in terms of the expected magnitude, distance to the source, and other parameters to the ground shaking levels or accelerations, as we know as engineers, to be used in earthquake resistant design. So these estimated accelerations or the design ground motions are used in structural and geotechnical analysis, in hazard maps, and in design codes. So they are very important features for us engineers. But the models that we use to estimate these numbers are only good as the empirical data sets. So if we look at the ground motion models, we can divide them into two different types. The first one is the global models that combine the data from the same tectonic regime. For us, for Turkey and Greece, the tectonic regime is the shallow crustal earthquakes in active tectonic regions. So if we combine data from different countries together, we will have a larger data set, which will be statistically more stable. The other option is to use the local models, which use the data from particular regions. For example, the model that Dimitri already showed uses the data from Greece, and we are going to show some models that use the Turkish strong motion database. These models will have smaller data sets, but they will be more representative of the regional characteristics. Which one to choose is a very controversial topic, and it's also very important because the one that you choose may change the design ground motions by a factor of 2. So it's an important decision. So the bottom line here is that each well-recorded earthquake is an opportunity to test the available models and our choices in ground motion selection. Ayşegül Hoca, next slide, please. The question is this earthquake well-recorded? Several colleagues show you that this earthquake is well-recorded. So the answer is yes. We will have several stations from Greece and 83 stations of AFAD that have rupture distances smaller than 200 kilometers. However, 17 of these stations from AFAD are deployed recently, like 3-4 years ago, and their site characterization is incomplete. So you may have a recording, but you don't have a site characterization. You won't be able to use that record in ground motion prediction modeling. In addition to it, from Turkey's side, we don't have any recording stations closer than 30 kilometers to the rupture plane. So this near field region is almost empty. However, we have 2 stations from Greece on Samos Island and 9 other recordings outside Samos within 200 kilometers. So in my opinion, this earthquake is a suitable candidate to test the available ground motion models. Next slide, please. Here, I would like to invite a PhD student from our department, Burak Akbaş, to explain you how we test the predictor performance of ground motion models and which models that we choose and analyze for this study. Burak, the floor is yours, please.
Thank you, Professor. Good afternoon, everyone. And so how do we test the predictive performance of the ground motion models? Well, simply we look at the distance attenuation plots and of course compare them with the recorded data from the stations. And to do that, of course, we need to select somewhat representative set of models. And there are quite a number of well-developed models. And from the global models of NGA-WES2, we selected 2 of them. And one is Chu-Yang 14 model, and the other one is the Boer et al. 14 model. And for BSSA 14 model, we also utilize the high Q and low Q versions as well. So a total of 4 global model. For the regional model, we have Boer et al. Newly developed 2021 model, plus we have Kale et al. 15 model, plus 2 of the Turkey adjusted version of NGA-WES1 model. And to get a good range actually, and when we think about the distributions of the data, and we selected 2 different VS30 values and 2 different Z-TOR values and created our plot. Actually, what we got is in the next slide, please. And what you are seeing here is the recorded data versus selected models for PGA. Actually, you can create these kind of plots for other periods as well. Actually, you should do that because there can be and there will be other behavior for shorter and longer periods. So here, overall, you can say that actually Dr. Sotiriadis mentioned that as well. The tested model are very consistent with the data, with the observed data for the distances less than 100, 120 kilometers. Next slide, please. And these are the plots for 0.2 second spectral acceleration. And not only for this period, but for the other period as well. There are some stations, there are some far field stations, and they are systematically lower than the median behavior. So they need to be studied. Next slide, please. And when you observe them, there are some stations at the longer periods, and these are the black dots actually. And on the plots, the lines are representing the prediction models, and the dots are the recorded data from the stations. And for this plot, the black dots actually belong to the Izmir stations. And at longer periods, they are systematically higher. And as my colleague mentioned, one of the reasons is actually the site amplification. And actually, you will find your answers in the next sessions as well. So actually, this was what I wanted to say. So floor is yours, Professor Askan. Thank you very much for your patience.
Okay, I would like to thank to all our speakers from Turkey and Greece. And I will conclude, actually, I do not want to repeat everything once again, but just highlight the ground motion part very briefly. We have been observing some long period spectral amplifications at stations which are located in the basin and our own softer soil stations. We see that there are longer significant durations at these stations with higher pseudospectral velocity values, which indicate, of course, potential basin effects. We see that the ground motion prediction models are usually, are mostly consistent with the data. They are predicting well, except of those stations that Burak has already mentioned. When we look at the structural failures, the weaker structures in Izmir area, even though they were really far away from the fault and they were collapsing, we see that their fundamental frequencies directly fall into the amplification range. Even though the ground motions recorded in Turkey are below the recent codes, we suspect that the buildings are very poor and they are actually shaken at that period range very much. When we look at the MMI distributions, we see that the maximum area is in Samos Island, as one would expect, and also in Bayraklı region, which indicate the potential damages and the collapses in that area. This actually concludes our chapter 3 talks and discussions from our side. I will now look at my watch. We have about 5 minutes to conclude this session. If there are any questions, Zeynep Hoca, are there any questions? I don't see them.
Professor Askan, sorry for interfering, but we got a message saying that we can raise our hand to ask a question. It looks like panelists cannot ask questions. So now the host let us to ask questions. And since we have time, may I ask a question?
Sure, sure.
Thank you so much. I would like to get your opinion on the contribution of this event, both from mechanism-wise, magnitude-wise, and the intensity of the recordings that we have on the ground motion prediction equations. How valuable is this event?
All right. That could be answered by me very shortly, followed by probably Zeynep. Well, I think when we look at the ground motion prediction models with the basin effects, we see that they are predicting closely, but we still are a little off the prediction models. And now I will give the word to Zeynep right now.
Ayşegül, thank you very much. I think one of the most important contribution of this earthquake to the ground motion modeling perspective is that this is one of the largest magnitude events that we see in Turkey with a normal mechanism. We don't have a lot of large magnitude normal mechanism earthquakes in Turkey. I know that there are some in Europe, but also in the United States, the number of recordings from normal events is very limited, especially large magnitude. So that would be the biggest contribution of this earthquake. And the second one is I agree with Ayşegül, the basin effects is not something that we really dealt with in the Turkish ground motion prediction modeling practice. So that's something we have to work on. And this earthquake provided us an opportunity to go over these artifacts of the ground motion, especially on longer periods. Thank you very much.
Zeynep, thank you. And we can actually try to model it and then make hybrid ground motion prediction models with our Greek colleagues, of course, and I'm sure they'll be interested. So that's one plan for the near future, Önder Hocam.
Professor, maybe Askan, can we get the Professor Basil's opinion as well?
Sure, sure.
If he's willing to.
Thank you very much, Professor Çetin. Actually, I don't have anything more to add in this discussion after Ayşegül and Zeynep comments. Only I will make a very preliminary comment. Now in Greece, we have started with our colleagues to study also the SSI effects in ground motion predictive models. So I think we can improve a little bit the qualification of this very useful tool. So in the near future, and also with the good collaboration that we have up to now with you, to improve our models in both sides. Thank you.
Thank you very much.
Do we have anyone raising hands? I don't see anyone. Are there any comments from the panelists about the effect of the ground motions? Well, I am sure the next talks, particularly on the soil response and the structural response, is going to complement what we presented to you.
I think there is one raised hand from Nikos Theodoulidis.
I am sorry,
No, it's okay. It's okay.
Okay, I think I saw Nico's hands, right?
Okay, sorry. Thank you. Thank you, Aegean. Thank you, Basil. Just one comment in the question of Önder. I think that one of the most important things that this event contributed is the cross-border collaborator area. That's the very important thing, and that we will build on this. We should build on this with relevant projects in the cross-border area, because the earthquake has not borders. So we will go on this direction. Thank you.
Thank you very much, Nikos. I think everybody agrees with you. Thank you so much. We share the same feelings and ideas.
This is, if I may comment, a great comment. We all fully agree. And with the chair permission, probably we can just have a few minutes break so that we can resume 15 minutes past the hour. This was a set of excellent sessions, and let us have a quick break now, and then we resume in 4:15 Istanbul time, 3:15 Athens time.